In today's video, I'm going to be talking about 3D vector moments. Okay, now here's a very engineering problem on the board, and the question says replace the loading shown by an equivalent. Replace the loading shown by an equivalent single resultant force, and specify the x and y coordinates of its line of action. What they are simply wanting us to do is to replace these forces 1, 2, and 3 with a single force, and then the distance of that force from the x and y axis, and not just any force, but the force will be in such a way that I will move these ones and put that single force at a particular point, and to produce the same effect as if all these ones are acting on it. That's what they want us to do. And to solve a problem like this, we make use of the vector moment, okay, and the right hand rule, of which I'm very certain majority of you haven't heard of it before. But I believe with this example, you guys will be able to understand and solve questions of the 3D vector moments. Okay, now the first thing I want to do is take the summation of the forces. So let's go. So to find that single force, I'm going to write sigma f of r, which I will call the resultant. I'm going to take the summation of the forces. Now, any force going upward, I'm going to use as positive. The one going downward, I'll take it as negative. So in this case, 100 is going upward. So I have plus 100 newtons. Okay, you have 400 going downward. So you have minus 400 newtons. And then we have 500 going downward. So we have minus 500 newtons. Okay, so what do we get in the end? Minus 400 minus 500, that's minus 900. 100 minus 900, that gives you minus 800 newtons. Now, this negative sign simply tells us that the resultant force is supposed to be going downward. So I should also be able to write it as 800 newtons with an arrow sign indicating that it is going what now? Downward. Now that's the resultant force, or that's the single force we're going to replace. But we are not just going to replace at any point, whether here or here. It has to be at a particular position in order for us to have a system that remains balanced like this. Okay, so if for example the distance, okay, of here to here, which is along the x-axis, I'm going to call it x. Here to here, along the y, I'm going to call it y. Is the point in which I'll place this 800 newton, okay, to get what I want. Okay, that is a system in which the 400, 500, and 100 newtons are removed and to make the same. I don't know, this point will be here, or anywhere at all. Okay, but what I want to do is look for that point. I will place 800 newton acting downward, okay, and to produce the same system. That now, how do we solve a problem like that? What we'll apply is the 3D moment what now equation. Okay, now what's the 3D moment equation? It's not a particular equation, we're going to create it. And how we're going to create it? We'll make use of what we call the right hand rule. Now, the right hand rule in this case, of course, there are so many right hand rules. We have the right hand rule for the for electromagnetism, in circular motion, and also in 3D analysis. Okay, that's in this case moments. Now, what we'll do is we're going to take our right hand. Okay, we're going to make a fist like this, with our thumb pointing outward and our other fingers curled in this direction. Now, it's saying if we are taking moment about a particular axis, okay, the thumb will point in the direction of the moment depending on where the other fingers are curled in. Okay, let me take a quick example. So if for example we're having this 800 newton acting at this point, I'm going to call here and draw the 800 newtons, okay, acting at this point, going to the plane. Here's what will happen. If we're taking moment about the x-axis, let me write it. Moment about the x-axis. Let's see what we're going to get. So for moment about the x-axis, okay, we're going to place our finger like this, such that this thumb is pointing in the direction of the positive x-axis. Remember, this positive x-axis, inside of it negative x-axis, positive y-axis, inside of it negative y-axis. Now it doesn't matter whether x or y are interchanged, depending on what is given to you in the question. Okay, so we're going to place our right hand like this, okay, and this one is pointing in the direction of the x, positive x. Okay, so since this thumb should be pointing in the direction of the positive x for moment, simply knows that any force that is coming out of the plane should be positive. So any force that is coming out of the plane going in should be positive, because if I place my hand like this one tells us the force and this one is positive moment. Okay, so that's what it's telling us. So if the force I'm dealing with is going into the plane, I should get a negative moment. So in this case, this guy will produce a negative moment because it is not coming out, but rather it is going into the plane. Okay, now moment is force and perpendicular distance, so I should be dealing with the moment, okay, in such a way that the force will be multiplied by what? The perpendicular distance from the axis I'm taking. So in this case, I'm going to get minus 800. Why is it negative? Not because it is going to the plane, but because I've used my right hand rule, and then I notice that I'm going to get a negative moment. So you have minus 800 times the distance from the 800 to the x-axis is y. So you have minus 800 times y. Okay, that's what we're going to get first. Now, what other force is in the equation? This one, but we've not removed it yet. Okay, so we have 500 here as well. Now, for this 500, it's going to the plane. So if we apply the same rule again, this one is going in, but anyone coming out to it also produce a positive moment. So this one will be negative. So you have 500 times the distance from here to here is given above. That's 400. 4 rather. So we're going to have minus 500 multiplied by 4 again. Okay? What other force is given? Now, here is another one, 400. Still going into the plane, right? It's still going into the plane. So we should be having minus 400 times what's the distance from here to here? That's also 4 now, right? Okay, also 4. Should be having times 4 as well. Okay, now what else again? And then we're having a force 100 newtons. Now what you notice is that this 100 newtons is lying along the x-axis. Please take note that whenever a force is lying along an axis, I am taking moment about that same axis, the moment should be equal to 0. Okay, so it's same as saying there is no moment that is being produced about now that axis. So in this case, we're going to have 0. So I'm going to say, okay, plus 0 moment and is equal to 0. Okay, so the summation of the moments about the x-axis is equal to 0. Okay, that's what we're going to get. Now, here is something. Most persons will make mistake while solving this equation. Okay, while solving the equation, in the sense that if we're taking moments about an axis like this, it should be the moment about the x-axis, okay, which is minus 800 times y, will be equal to the other moments. That's what we should be getting. Okay, so if I should solve with minus, minus, and plus like this, I will get a wrong value. So what I will simply do is either well, I'm going to make it easy. What I'm going to do is, instead of switching these signs to positive, okay, which gets you more confused because we already used negative, the right hand one, we'll see that it's negative. What we're going to do instead, okay, here's what I'm going to do. I'm going to say minus 800y is equal to, okay, is equal to minus 500 times 4, okay, minus 400 times 4, okay, then plus the 0 which we obtained, or minus 0, it doesn't really matter. Okay, now that is what we're going to do. So if this in this case, I believe everybody trying to solve a problem like this should not have any problem doing this thing. Okay, so what we're going to do from here is we're going to find y. So have minus 800 y equals this multiplies to give you minus 2000, okay, minus 1600 16,000 rather, 1600, okay, and then from there y is equal to minus into brackets, that should give you 36,000 if I'm not mistaken, or 3,600 rather, divided by minus 800. So minus cancels out minus, this 0 takes out this to 0. So 8 into 36, what should that give you? 8 into 36, that should be in decimal, okay. So 36 divided by 8, that should be 4.5. Alright, 4.5 meters. So the distance we need to place the force from the y-axis should be 4.5 meters. Now how about the x-axis? We're basically going to apply the same rule, okay? We're going to apply the same rule. So for moments about, to get that of x, we're going to take moments about the y-axis. So now taking the state force again, 800 is going to the page. So if I put my hand like this, any moment that is going to the page should produce a positive moment, because here is positive, okay? This is positive y. So any moment there's any force coming to the page should produce a positive moment. Hence, this 800 is going to give us a positive moment. What is the distance from 800 to the y-axis? That's x. So I'm going to have plus 800x equal to, do not make the mistake of leaving out the equal to just like we did in the first time. If you do that, you're going to get a wrong answer. Okay, so I'm going to get plus 800x, okay, and that will be equal to, what are we going to get now? The other forces, in this case, this one is going to produce a 0 moment because it's along the y-axis. Now how about this one? It's going to produce a positive moment. Applying the right hand rule, see, it's going inside, and here is a positive y-axis. So it's going inside, we're having 500 newtons. Okay, what distance from here to here? That's 4. So we're going to get 500 okay, times 4, and then for this other one 100, okay, this one is going to produce negative moment because it's going out of the plane, but according to the right hand rule, anyone coming inside is also going to produce a positive. So 100 times the distance from here to here, that's 3. So I'm going to have minus 100 times 3. So from here, the distance x is equal to multiply, that gives you 2000 minus 300 divided by 800. So we'll do that in the calculator. We're going to get 2000 minus 300. That's 1700 divided by 800. That will give us 2.125 meters. So we have 2.125 meters. So basically, the force we need is a single force having a magnitude of 800 newtons into the plane, because we could either apply the force pulling it out or going inside. So once a force that is going into the plane, at what distance? From the x axis, it should be at a distance of 2.125 meters, and from the y axis, it should be 4.5 meters from the y axis. So from here to here should be 4.5, and from here to here should be 2.125. So basically, the aim of this video is to help you understand how we make use of the 3D moment, or the right hand rule in particular. So you can see how we manage to apply the right hand rule to solve a problem like this. Okay, we had to make use of our right hand following the principles of moment, okay, using the right hand rule to get the distance between the distance of the force which we are going to place there to the x axis, okay, this x axis, and then to the y axis. So it's quite easy. And on next video, we'll solve a few more problems, and I would like you to subscribe as usual. I'll take time to go through our other videos, and also do it to click on the notification bell so that when a new video is being uploaded, you'll be one of the first persons that get notified. Okay, the YouTube channel name remains Dr. Flash. See you in our next video.